Okay, we're continuing with Chapter 3 in the trigonometry textbook. We've talked about radian measure and applications of radian measure. Now we're going to talk about the unit circle. So the unit circle is probably the most important topic in all of trigonometry. Well, actually, I don't know if I'd say it's the most important, but it's a topic that once most people are done with trigonometry, if the subject ever comes up again, the first thing that a lot of people think about is the unit circle. But I would consider the most important topic in all of trigonometry to be the general definition of trig functions. So, okay, but what is the unit circle, and why is that typically the first thing someone thinks about when they think back to trigonometry? Well, before we get into this, you might be wondering, well, what's circular functions about? You know, this section is the unit circle and circular functions. I'll explain circular functions in a little bit, but let's focus on understanding what the unit circle is. So imagine you've just taken trigonometry. One of the main things you learned is the general definition of a trig function. So you understand the inherent meaning of a trig function. And now let's imagine it's a time period before calculators. Even though you understand the meaning of trig functions and how to calculate them, it would be nice if there was a quick kind of shortcut method to get trig function values, to pull them quickly. And even post-computers, even in times like today with calculators, imagine that you're going to be one of the people that are writing the code for a calculator or a computer with trig functions, the code to evaluate trig functions. You already understand trigonometry. You know the meaning of trig functions. But again, it would be nice if there was some shortcut, efficient way of calculating trig functions, trig function values. That's the purpose of the unit circle. Okay, so you see what I mean, how, you know, I don't want to say it's the most important topic, because if you don't understand the inherent meaning of the definition of trig functions, then what's the point of understanding the unit circle, right? But it still is a very popular topic from trigonometry that is one of the first things that's mentioned or talked about when trigonometry comes up. Okay, and so here's the unit circle. And once you're done with trigonometry, you really should be able to reconstruct this entire circle with all of this information on it at the snap of a finger, just at any moment. If someone says, construct a unit circle, you should be able to draw this out and put all this together. No problem. Now you might think, well, man, that's a lot. All this information here, I'm going to have to memorize all of this. No, because what you're about to see is that the way this is set up and defined, the only thing you're going to have to memorize is, if you would sit down, blank piece of paper, and you're going to draw this entire unit circle, you need to first, from memory, draw a 30, 60, 90 triangle with the ratios of the sides. So that's, draw this. So 2, 1, root 3. So 30, 60, and a 45, 45, 90 triangle. This is the only thing you'd have to memorize. Well, you have to know that the special angles are 30, 60, and 45. I think that's easy. But then you got to draw a 30, 60, 90 and a 45, 45, 90 triangle, and you have to have these sides memorized. If you know this, then you can put all of this information shown here without having to memorize anything. I mean, other than the concept of what it is. Okay, so how is that possible? How could we construct this entire diagram here with all of this information without having to memorize anything but just these base triangles here and their side length ratios? Well, that's what the unit circle is all about. So, okay, let's start with the general definition of trig functions. We've gone through this derivation of trig functions, this definition many times, but the more repetition, the more times we do this, the better. You can't do this too many times. This is the whole purpose of this course, pretty much. So the general definition of trig functions. You draw an XY coordinate system. Then you think about any angle measured from standard position. So standard position, the terminal side is along the positive x-axis, or no, the initial side is along the positive x-axis, the initial side, and then an angle is measured positive from this side to the terminal side in the counterclockwise direction. So let's just draw any angle in any quadrant, just some random angle. Okay, and I'm purposely making this ray here and this ray just random lengths because the lengths don't matter, right? When you think about an angle, the lengths of the sides have nothing to do with anything when it comes to an angle. The only requirement for an angle is these two straight sides, the sides are straight, and this in a vertex. A vertex that you're this opening between these two straight sides is it's you think with an angle it's a rotational opening, a rotation about the vertex. That's all an angle. That's what an angle is, and that's it. Okay, so here's this angle. We'll call it theta. Okay, now so we're defining trig functions, right? What are the trig function values of this angle theta? Well, the next thing you do is you pick any point on this terminal side, any point. The point doesn't matter whatsoever. Let me extend this. So we're just going to pick this point. Okay. Now, from that point, you make a right triangle with the perpendicular attached to the horizontal axis. And this is the same exact rule for the same exact process for an angle in any quadrant. Okay. The distance from the point to the origin, we call that R. And then the side lengths of the triangle, you just label as X and Y, so the coordinates. You label as this point has coordinates, right? And so the side lengths of the triangle are like the coordinates of the point. So those coordinates could be negative. Like in this case, X is negative, Y is positive. In another quadrant, it'd be different. But the radius is always positive because with the Pythagorean theorem, R is the square root of X squared plus Y squared. It's always positive. Okay, now if you come inside the right triangle, there's these two acute angles. The acute angle of the right triangle that has vertex at the origin, that's called the reference angle, theta prime. In general, you don't really care about the value of the reference angle unless it helps you to determine what the magnitudes of the side lengths are, the magnitudes. For example, if this was a 30-degree reference angle, well, then we could come to our reference triangle and it would give us the magnitudes of the side lengths, the magnitudes. Now, I'm saying magnitudes because, with an actual right triangle, the 30, 60, 90, and 45, 45, 90, the actual right triangles we construct, this is just a construct inside of this coordinate system, but a literal right triangle doesn't have negative side lengths. But in the definition of trig functions, they can this is a construct. So if you had a 30-degree reference angle, you could get this was, so it would be, this would be minus root 3. This would be 1, this would be 2. But other than that, you're not really concerned about what this angle is. All you're going to do is from here to get the trig functions of this angle, this is the angle that we're considering, you come to the position of the reference angle and you do SOHCAHTOA, honoring the signs of the potential negative signs of X and Y. And so with that, the sine of theta is, so go to the reference angle opposite over hypotenuse. The cosine of theta, go to the reference angle adjacent over hypotenuse. The tangent of theta, opposite over adjacent. And then cosecant, secant, and secant are the reciprocals of these values. So cosecant and that's it. That is the definition of the trig functions. If you don't understand this, then there's no point, in my opinion, of understanding this. Because if this is the only way that you know to understand the meaning of a trig function, then you're going to think that you have to have a circle to define a trig function. That's incorrect. Circles or a circle has nothing to do with the root definition of trig functions. Nothing. The root of trig functions is angles and right triangles. You can't evaluate a trig function or understand the meaning of a trig function without an angle or without a right triangle. Okay, so now the unit circle. What the unit circle does is it condenses and simplifies this definition to allow you to obtain trig function values quicker, easier, more efficiently. So I imagine before calculators, before computers, engineers, mathematicians, etc., either always had a booklet with a big table full of trig function values going from 1 degree to 2 degrees to 3 degrees, etc. They had that, and then they could draw the unit circle on command. So they could pull trig function values from any special angle, 30, 45, 60, or any angle that had a special angle as a reference angle. But again, if they had a big table of trig function values, like with a half of a degree, 1 degree, 1.5 degrees, 2 degrees, whoever made that table, I would be willing to bet, made that table using like numerical estimations with the unit circle, not the general definition. You know, if you didn't have a calculator or like a table and you wanted to find an accurate approximation for the sine of 113 degrees or the cosine of 113, etc., you would go to the unit circle and estimate it from the unit circle. That would be more efficient. That would be easier to do. Okay, so why is that the case? What is the unit circle? Okay, so what you do is, starting from the general definition, we say that, okay, we're going to make a constraint on this definition. The constraint is that we're going to make a new rule. The new rule is that, so everything is the same as we just laid out, but when you come to the terminal side, you can't just pick any point you want. The rule is you have to pick a point that results in this radius being 1 for any angle. And for any angle in all 4 quadrants, you have to pick a point on the terminal side where the radius is 1. Okay, so let's start again. The general definition, you draw the XY coordinate system. Now with this rule about the radius, that means there's a group of points that are only valid to pick for the top vertex on the right triangle. There's only a group of points that are valid as a selection in the entire 3D plane. That group of points is on a circle. And it's on a circle that has a radius of 1, a unit circle. That's why it's called a unit circle. The center of the circle is at the origin, and the radius is 1. With this constraint on the general definition, for any angle, so here's the initial side. Okay, so you pick any angle, 0 to 360 or negative angle, whatever, but the terminal side is going to be located somewhere in one of the 4 quadrants. Okay, but wherever that terminal side is located, the point that you pick on the terminal side is going to have to be, it's going to be on this circle, no matter what, with that constraint, right? So let's put this out here. So if this is the angle, there's the terminal side. Now, usually the next step would be we pick any point we want, but with the constraint, the point has to be this point. And the radius is going to be 1. And in fact, let me redraw this in the first quadrant. I don't want to get too far ahead, so let's start in the first quadrant. So here's the angle. Okay, so the angle constrains this terminal side in this direction. Usually with the general definition, we could pick any point we want, but now with this new rule, we have to pick this point. Okay, but again, I really want to stress that we've made this rule here. So the radius is 1. We made this rule here, but this has nothing to do with the actual definition of the trig functions at all. You do not need this circle to define trig functions. We're just adding this rule for the sake of creating this trig function kind of table that you can think about, that you could pull trig function values from. easily. Okay, next step, we draw the right triangle with perpendicular attached to the horizontal. Okay, then this point has coordinates, and the coordinates of that point dictate the side lengths of the right triangle. Okay, so what has this done? Why did we do this? Well, okay, now if we rewrite the trig function definitions, well, r is equal to 1. So sine of theta is equal to y, cosine theta is equal to x, tangent theta is equal to y over x, and then you have the reciprocals. Okay, so but there's one reason you can see that this is nice, how this cleans up the trig function definitions, is that the r is 1. You know, it simplifies these formulas with the radius, forcing the radius to be 1. But also something else you might have noticed that's interesting is that the coordinates of this point on the unit circle corresponding to this angle, the coordinates are equal to the sine and the cosine of the angle, right? The coordinates of this point, x, y, well, x is cosine theta, y is sine theta. In general, that's not the case because the radius, if the radius isn't 1, then it's the cosine is the x value divided by, you know, if this circle was 3, the radius was 3, it would be x divided by 3. But since it's 1, you get the cosine, this coordinate here is actually equal to the cosine. This x coordinate and this y coordinate is actually equal to the sine. Now, there's nothing kind of cool with coordinates like that works out that way for the rest of the trig functions, but still, once you see the coordinates, you know the coordinates are the cosine of the angle and the sine of the angle. Well, you know that tangent is sine divided by cosine, so you could just say this divided by this, and then you know the other trig functions are the reciprocals, so it's pretty cool that the coordinates give you like the two, I guess you would say the main trig functions, the starting trig functions, sine and cosine. Okay, so that's it. That's the unit circle. But we're not quite done. Let me illustrate to you how you could easily construct this entire diagram on command without having to memorize anything except for these base triangles and their side lengths. And then just you have to recall the general idea of what the unit circle is. So what you do is you sit down with a blank piece of paper, you draw out these two right triangles, then you make your XY coordinate system, and you put a circle of radius 1 centered at the origin. Okay, and then the goal is to put all of the information for every single special angle, every single quadrantal angle, and then every single other angle that has reference angle that's one of the special angles, which sounds like a lot, but this is going to take way less time than you think because of another advantage of this unit circle trig function setup. Okay, so you're going to start in the first quadrant. Okay, and the goal is what we want to do for each of these angles in the first quadrant and the quadrantal angles at the positive x and positive y axis is we want to mark the point on the circle that corresponds to the angle line. So, you know, this is the 30-degree line, for example. We want to mark that point on the circle, and then we want to indicate the degree measure of that angle. So what is this angle here? The angle that corresponds to this point in degrees, you put that in degrees, and you also put it in radians. And then on the other side, we want to put the coordinates of the point. That's the goal. We want to do that for every single special angle and the two quadrantal angles in this first quadrant region here. So the 30-degree point on the circle, how do we mark this point? Well, since this is the unit circle setup, we know that the coordinates of this point, or the coordinates of the point that are going to correspond to 30 degrees, are going to be the cosine of 30 is going to be the x coordinate, and the sine of 30 is going to be the y coordinate. So You come to your triangle here, cosine of 30, adjacent over hypotenuse. This is going to be root 3 over 2, positive root 3 over 2. And then the y coordinate is going to be opposite of hypotenuse, 1/2. So you put the coordinates. You don't draw the line first because you don't know. How do you know what 30 degrees is? You can't draw the line and then mark off the point. You can't draw the 30-degree line, then mark off the point. No, you have to, you don't have anything written. This is blank. You don't have anything on here. This is completely blank. You start by saying, okay, I'm going to put the 30-degree point. You know its coordinates because this is the unit circle setup. The coordinates are x coordinate, root 3 over 2, y coordinate, 1/2. So on your grid, you mark off this point on the circle as close as you can. You mark this point off. Then, now that you have the point marked off, then you put 30 degrees and pi over 6 in the coordinates. Okay, where's the point on the circle that corresponds to 45 degrees? Same thing. What about 60 degrees? Same thing. Mark off the point and put the degrees and radians angle. Now, the quadrantal angles are easy. This is just going to be 0 degrees, 0 radians, coordinates 1, 0, right? You know it's a unit circle. Same thing with this quadrantal angle. Okay, so now you've got the first quadrant all labeled out. So now do you have to go through this process for the entire rest of the circle? Well, it wouldn't be that big of a deal to do that, but there's a shortcut. Okay, a circle like this, any circle centered at the origin, is symmetric with respect to both axes and the origin. It's fully symmetric. It's like in the sense of a function, it's both even and odd. So what that means is that for any point on the circle, so let's say we're in the first quadrant. So you got a positive x and a positive y, but this applies to any point. But let's just say we're in the first quadrant, any point on the circle. It has an x and a y coordinate. Because this is fully symmetric with respect to both axes and the origin, that means that the point minus x positive y is going to be on the circle. The point positive x minus y is going to be on the circle. And the point minus x minus y is going to be on the circle. Okay? And furthermore, if any angle in the second, third, or fourth quadrant that has a reference angle equal to an angle in the first quadrant, so let's just focus on the special angles. So any of these angles that has a reference angle that's equal to one of these angles, they're going to have the same exact magnitude of coordinates, but just different signs. So 120 degrees, that has a 60-degree reference angle. Look at its coordinates. Minus 1/2, positive root 3 over 2. You see? 210, that's a 30-degree reference angle. So if we come to 30 degrees, root 3 over 2, 1/2, minus root 3 over 2, minus 1/2. So you can see that to mark off any of these points in the second, third, or fourth quadrant, you don't have to keep coming back to your reference triangles here. You could just go pull from the coordinates of these points. And whether or not you make the x coordinate positive or negative is easy because you can see what quadrant you're in. Second quadrant, negative x coordinate, positive y coordinate, etc. Okay, and that's it. I'm going to make a separate video where we construct the unit circle from scratch, this entire unit circle, with all the special angle information on it. Okay, but before I end the video, I want to point out that, so yes, these are just the reference angles, right? And I mean, in general, we're always going to go to our calculators anyway, even for reference angle values. So you might be thinking, well, what's the purpose of the unit circle? You know, we just use our calculators now, right? Well, okay, but someone needs to program the calculators, right? And I would be willing to bet that anyone that is programming a calculator, trying to put an efficient code for estimating a trig function value, is going to use the unit circle, this efficient setup for pulling trig function values. Because if you're estimating whatever this is, you know, you want to estimate what's the sine, cosine, etc. of 17 degrees. Well, with the unit circle, you're taking out a lot of steps that would be present with the general definition. You know, you just need to find coordinates. All you have to do is find coordinates of this point. I guess you'd have to numerically dial in the angle, and then you're just finding coordinates of the endpoint of the angle, right? There's less steps, less error stack up. It's more efficient. It's easier. So this is the most efficient way of obtaining trig function values. But again, the definition of the trig function, the definition, has absolutely nothing to do with a circle, a unit circle, any circle. This is the general definition of trig functions. Okay, in the next video, I'm going to talk about what circular functions are all about, and how, for the most part, we're not going to pay much attention to this idea of circular functions.